Okay, welcome to double integral video. Before I start double integrals, I would like just to uh, recall what is integral, why we use integrals for. Suppose we have x-axis, y-axis, right? This is y-axis. This is y-axis and this is the x-axis, right? And suppose we have a given curve, f of x, a part of curve f of x above the x-axis, and we need to find the area limited between this curve f of x and, let's say, between the area limited. Let me draw it, and let me say we need to find this area over here between f of x and the x-axis, above the x-axis. And over here, these two vertical lines of, let's say, x equal a, x equal b in general, and I need to find the area limited over here. I need to find the area limited over here. I need to find this area over here, right? This shaded area. All right. What we do is we divide this shape here inside. Since we have curved side, it's not perfect line, right? Straight line. We have the area I need is the region between these two straight lines and this straight line too, but this is not straight line, so it's not rectangle. But if I do very tiny small rectangle, let me do it in another color, red. If I do very small tiny rectangle over here, very small rectangle, okay, this rectangle has length or width. This width here is dx, because it's difference between 2 points on x-axis, right? It's x1, x2. So it's x2 minus x1, this dx, but it is very small distance between x1 and x2. So very small dx, right? Very small dx. And the height of this rectangle, is simply this point here, which is f of x, If I know the height, if I know the width of the rectangle and the length or the height of the rectangle, so what is the area will be? The area of the rectangle will be equal to width times height, or width times length, which is f of x times dx. But if I need to find, okay, and this, and why I said this is a rectangle, because the small dx I took makes this curved line looks like a straight line, because it's very small. How many small rectangles do I have inside this area? I need to find this region. I need to find its area. We have maybe infinite number of rectangles, So to do so, to find this area, of the shaded region, I need to have the sum of the areas of every single small rectangle I have inside over here. So we can do many rectangles over here, many rectangles, right? Let's consider each line is a rectangle. Each red line I'm drawing is a rectangle, right? Of width dx, very small width, and that makes this curved line looks like a straight line, and dx will be the width, and f of x will be the height, right? If I add all of these, this is the purpose of having integrals, definite integrals, because the lower bound of this integral is a and the upper bound is b. So I need the integral from point A to point B right? I need this integral from point A to point B, from x equal A simply to x equal B of f of x dx. And we find the area of the whole region that way. Why I'm saying that? I'm saying that because the same thing exactly is we are going to see if we are working with three-dimensional. Let's draw three-dimensional. Uh, let's draw three-dimensional x, y, and z. X, y, and z. This is that. Okay. So this is that. Let's do this x and this as y. That's great. Suppose I have a certain cube or shape here, solid shape, in a three-dimensional shape, right? Three-dimensional shape. This point is 0, this point is A, and this point is B. Let's do draw. Let me draw in red. Let me start from this point in Z. Draw this curve. This curve, for example. Let's draw this curve and this curve. Okay, this is the side of the square of the cube or of the solid shape. Okay. I need to find the volume of this solid shape, right? I need to find the volume of this solid shape. That's great. That's nice. What I do is, it depends on what is variable and what is constant. And I will do it in all three ways. I will try to fix, I will try to fix, I will try to take y as constant, and we take z. Z is function in xy. As we have here, z is a function in xy. As we have here, y as a function of x. X is whatever you give value for x, it gives you a different value of y. So when x change, y will change. The same here. Let's say y is fixed first. Let's do a fixed y over here. Let's take a fixed value for y. Let me try to do it in another color. Okay, fixed value of y. And let's draw a sheet of paper inside. Sheet of paper here. It has a given y. It has a given y. And it has, let me draw first a sheet of paper. On this, okay, let's draw this sheet of paper first. All right, this sheet of paper over here, if I can find its area, and we do summation of all areas parallel to this sheet of paper, it will give me the volume of the whole solid, exactly like I did over here. Exactly like I did over here. So the area of the sheet of paper, right? Uh, uh, the summation of areas, of infinite areas, because it's very, very tiny sheet of paper. How to find the area of this sheet of paper? All right, let me change the color and we'll see. Let's fix y first, and let me take differentiation here in the x. This is the x, okay? If you can see it, this is the x, and this is the x, and we can, okay, time will be over. I will continue in the other video.